At this point, I'm assuming you already have the basic idea of working with absolute extrema and you understand the big picture. At this point, I thought it would be good to sort of look at some special cases where things work a little more nicely. And the first of those is what I'd call the absolute simplest case. And that's if you have a continuous function f over some closed interval a to b. So continuous over a closed interval. Those are the two conditions. If you have that, that is really the simplest possible case. In order to find the absolute extrema for that case, the first thing you want to do is do what you always do when you're finding relative extrema, and that is take the derivative of the function, set it equal to 0, and find your critical numbers. If there are any critical numbers that fall outside of the interval from a to b, then you don't consider those, but then you keep all the ones that are inside of the interval from a to b. Then you calculate the y value for each of those critical numbers, however many you had that were inside the interval a to b, and you also calculate the y value of both interval endpoints. Now, from all of those sets of y values, the largest one is going to be the absolute maximum of that function over the interval from a to b, and the smallest y value is going to be the absolute minimum of the function over the interval a to b. In other words, the simplest case, it's very mechanical. You don't really have to overthink it if you know you have a continuous function over a closed interval. For example, suppose I had the function f of x equals 3x cubed minus 9x over the interval from 0 to 3, the closed interval from 0 to 3. I've already carried out the first step, which is taking the derivative, setting it equal to 0. I don't want to focus on the mechanics here because I'm assuming you've already got that under control. If not, you can go off to the side and stop this and deal with that. I want to look at the big picture. So I go through the process and I find my critical values. Notice that I get positive 1 and negative 1 for x. Those are my two critical numbers. But the interval I'm interested in is only the interval from 0 to 3. So I'm not going to consider the minus 1. The minus 1 gets eliminated, not because it's negative, but simply because it's not in the interval that I'm interested in. So the only one that I'm really keeping is x equal to 1 because it is in the interval that I'm looking at. Okay, step 2. Step 2 said to calculate the y value for each of the critical numbers. There turned out to just be 1. Remember, I had to toss the minus 1 because it's not in the interval and just keep the 1. So I calculate f of 1, but I'm also calculating the y values of both interval endpoints. So I'm going to calculate the y value for the left endpoint, which is 0. That's f of 0. And I'm calculating the y value for for 3, which would be f of 3. Notice that I'm calculating the y values by going back to the original function. I'm going to the original function, not the derivative. So that's a common mistake. When you're calculating y values, you always go back to the original function. Again, I'm not focusing on mechanics here, but you can pause and follow that through if you want, if you like. The point is, when you evaluate the function at 0, you get 0. When you evaluate the function at 1, you get negative 6. When you evaluate the function at 3, you get 54. So that's step 2. Finally, step 3 says, from what you've done in step 2, look for the largest y value, and that's going to be your absolute maximum. So if you look at the y values of 0, minus 6, and 54, 54 is the largest of those three y values, so that is the absolute maximum. It occurs at x equals 3, but the absolute maximum itself is 54. Then you look for the smallest y value. Well, obviously, negative 6 is the smallest of the y values. So negative 6 is the absolute minimum, and it occurs at x equal to 1. The absolute minimum is negative 6, and that negative 6 occurs when x is equal to 1. This is the absolutely simplest case for finding absolute extrema, but it applies anytime you've got a continuous function over a closed interval. It's a very simple case. You could probably make dozens of simple special cases, but I will talk about a common special case which is easy to handle. And that is when you have a continuous function, just as before, over an interval which doesn't have to be closed here, but it does have to have only one critical number in the interval. So if you're looking at a continuous function over any interval and you found out that there's only one critical number in that interval, then this special case applies. And if it does, of course you can't really tell until you've done some preliminary work, so you're going to start off just as before by taking the first derivative set equal to 0 to find your critical numbers. You're always going to end up doing that anyway. Now if it turns out there is just one critical number in that interval, then you want to continue. If not, this special case doesn't apply. But assuming you get past step 1 with only one critical number, then you'll go back to what you were doing when you were studying relative extrema and use either the first or second derivative test to figure out if that critical number is associated with a relative maximum or a relative minimum. It turns out that if that single critical number, there can only be one in that interval, but if that single critical number happens to be associated with a relative maximum, and you find that out by using the first or second derivative test, but if it turns out to be associated with a relative maximum, then that relative maximum is also the absolute maximum on that interval. And if that single critical number happens to be associated with a relative minimum, again by having used the first or second derivative test, then that relative minimum is also the absolute minimum on the interval. Now, a couple of things. First of all, this only applies, this is a very special case, but it's fairly common, but it only applies when you have a continuous function over an interval where there's only one critical number in that interval. If you have two critical numbers in that interval, this doesn't work. The other thing that I would say is this only tells you about one of the two absolute extrema. Since you only have one critical number in the interval, this procedure doesn't say anything about finding a second absolute extrema. So if you go through this procedure and find out that you have an absolute maximum, this procedure doesn't tell you anything about whether you have an absolute minimum or not. And if you go through and find out that you have an absolute minimum using this procedure, you still don't know whether you have an absolute maximum or not. You have to use some other analysis, but it does help you find one of them. And this is a very common situation, especially with word problems where you're going to have, or application problems where you're going to be solving and trying to minimize something or maximize something. Typically you fall into that case. Quite often you do, at least. Now, I suppose I might want to say a little bit about why this might be true. I guess you don't need to know that just to be able to use it, but if you just play around with a curve, you can sort of see how that might be true. If you have some curve like this that only has one critical value, then if it opens like this, that critical value is not only going to be a relative max, it's also going to be an absolute max. It could also look something like that. Again, you've got one critical value and it turns out to be a relative minimum, and that relative minimum turns out to also be an absolute minimum. You can play around with these things. You say, well, what if it does this on one side and then goes the other way on the other side? But if it's a continuous function, the only way you can make it behave like that is for it to turn around. Well, once it turns around, now you have two critical values, and this special case doesn't apply. So if you play around with different things and try it, you'll see that you can't draw a continuous function with only one critical value that doesn't have that critical value either being a max or a min. Just can't do it. So anyway, that's a special case. As I said earlier, you could probably make up several special cases that work with different things, but rather than do that, I'm going to say this. You could develop lots of these special case scenarios and work them out for each one, but it sort of gets to the point where it's not worth the trouble. But what I'd probably say is that if an absolute extrema problem doesn't fit into one of the two special cases that I did point out, it may just be the best idea to just go off to the side and get a sketch of the graph and spend whatever time you need to figure out what the graph looks like, and then you can answer the question. So you spent quite a bit of time earlier learning how to graph rational functions and polynomial functions and piecewise continuous functions. So you go back and use those skills. So if you get a problem, a function that doesn't fit into one of the two special cases that I mentioned, it might be that you just take the time and graph it. So suppose I got a problem and I said, oh, okay, it doesn't fit into one of the two special cases, so I'll just graph it, and you come up with this graph. Once you get the graph, you're really home free, because the highest place on the curve, the highest point on the curve is where the absolute maximum is going to be. And you're looking through here, the lowest place on the curve is going to be where the absolute minimum occurs. So once you get the graph, you can see, and on this one, the absolute lowest point on the curve is here at A, so the absolute minimum occurs at A. And there is no highest value because that's not a closed interval. You can get closer and closer and closer to that point, but not actually ever get there. So we've talked about that earlier as well. There is no absolute maximum, but there is an absolute minimum. And the third possibility, if you graph it and you find out it's a rational function and its graph looks like this, you can immediately see that the curve runs up the vertical asymptote and doesn't turn around, so there's no absolute maximum. And then over here it runs down the asymptote and never ends, never keeps going, never turns around again, so there's no absolute minimum either. And again, the point I'm making here is if the problem doesn't fit into one of the other special cases that I talked about earlier, perhaps the best thing to do is just take whatever time it takes to sketch your graph and then use the graph to answer the question. I think that would be my recommendation in most cases.